All right, let's turn to the final problem set, which is about 0-1 programming. And that should be pretty fast because there's nothing that we really can do in terms of graphical analysis. So anyhow, the problem is that the city of Broketown needs to do repairs at some of its public facilities, specifically the aquarium, the bathhouse, the convention center, the docks at the marina, the electricity grid, the football stadium, the golf course, and the hospital. Doing the repairs is essentially to restoring the city's tax base. In order to do the repairs, the city is constrained by its budget, machines, local labor force, and public planning support staff. Below table summarizes the increase in tax revenues when any of the public services is restored. It also shows the resources needed to realize each project as well as the maximum available resources. Which projects should be realized to maximize the restoration of tax revenues? Okay, so we have projects that go from A, B, C, D, E, F, G, and H. And we need to find, as always, the optimum quantity. And then what is normally the unit profit is in this case the tax, I just call it the tax contribution. And here we have for A, it's 80, 85, 75, 95. You just can copy that 65, 70, 100. Okay, A, B, C, D, E, F, G, H. So I must have forgotten one. 80, 85, 75, 95. Well, D is 95, E is 90, 65, 70, 100. And then we have the various constraints for A, B, C, D, E, F, G, H. So we have a budget constraint, machines, labor force, and support staff. Okay, so we can just copy those coefficients. So for A, 30, 30, 50, 10, 30, 30, 50, 10. For B, 30, 20, 20, 40, 30, 20, 20, 40. Then for C, 40, 35, 35, 40, 35. D, 10, 45, 20, 40. For E, D was 10, 45, 20, 40. For E, actually I think I probably just can copy this one. That's probably safer. Yeah, much better. And then let's just copy and paste the format. Okay, so that was much faster. And let's make it. So in this case, maybe we can fit to content to gain some real estate. Okay, so now the profit function, or maximum profit, or maximum tax. And so we need still the total usage. Total usage. And then the sign. So the sign here is always less than or equal. So that makes it a little bit easier. And then we have the maximum available. Okay, so we have 200, 180, 160, 140. Okay, so everything that we entered so far is an input, it's all given. So we can use the cell style for an input. And here I just initialize everything with 0 for the optimum quantities. So that will be an output that will be generated by Excel. So I format that as an output. And the total usage and the maximum tax. We use the sum product formula, sum product. So that will multiply the optimum quantity by the tax contribution. So if I click in F, for example, 1, the maximum tax goes up to 65. So that formula, that's a calculation. And then we have a few more calculations left, namely the total usage. So we use again sum product. Okay, because I want to copy down that formula, but I don't want to have the optimum quantities change, so I anchor those with F4. And here we have to go till J. And I can copy this down. Yeah, that's it. So now we can program everything. I mean, we can run it. And we see, if we go to data, solver. Let's reset all. So I want to maximize my tax by changing those cells, and my constraints add, because they have all the same sign, I can just click into the first and drag it down. And then I also click into the first cell of the maximum available and drag it down. And again, we have simplex, linear. And if we just don't do anything, we probably get weird results. So keep solver solution. Okay, so now it says, you know, we should fix 2 aquarium and 1 bathhouse. And I just also saw we still want to format the maximum available as an input. But because it is a 0-1 decision, we cannot build 2 aquariums and restore 2. And we could do 1 bathhouse, but we have only 1 dog. So we need to tell Excel to please use the binary solution. So we go back to solver, and we need to add 1 more constraint, which is that the optimum quantity cells, they need to be binary, 0-1. Okay, and then we solve it, and we keep the solution. And now the optimum solution would be to fix the aquarium, then see the convention center, no, not the convention center, the docks, then E, the electricity grid, and the hospital. That would be the best plan. But you see, when it comes to 0-1 programming, we pretty much rely exclusively on Excel. Okay, so that's it with linear programming, and I hope you found it interesting, and let's just stop here. So